Good evening, dear past presidents, council members, members of the ISL staff members. This is a hybrid meeting and most of our members are joining online. Only a limited number of participants were invited physically to take part in this event. So you all are kindly, cordially welcome, or warmly welcome to the event. This is the 35th memorial oration of late Professor E.O.E. Pereira. Kindly arise for the presidential procession. Yeah. To start the event, let me invite the following dignitaries to light the traditional oil lamp. Engineer Dr. Kamal Laksiri, the acting president of IESL. The two senior most past presidents, Engineer Mr. Pial de Silva, Mr. Chula de Silva. Our speaker today, Professor Janaka Vijayatunga, Engineer Manjula Samarasinghe, the Secretary to Civil Engineering Sectional Committee, and myself. I also invited our immediate past president, Mr. KPIU Dharmapal, also to light the oil lamp. Thank you very much. Kindly remain standing. Our next item is to garland the photograph of late Professor E.O.E. Pereira's photograph. I cordially invite our acting president, Dr. Kamal Laksiri, to garland the photograph. Thank you very much. Kindly be seated. So, to start the event, I invite Dr. Kamal Laksiri, the acting president, Professor Janaka Vijayatunga, our speaker today, and Engineer Manjula Samarasinghe, the Secretary to the Civil Engineering Sectional Committee, to the stage. Thank you. Now it's the time to deliver the welcome speech. I invite Dr. Kamal Laksiri, the acting president, to share a few words with the gathering. Or to Thank you, Engineer Neil, CEO. Good evening to all of you. As the President-elect and the Acting President, I am honored to welcome you all on behalf of the Institution of Engineers Sri Lanka for the Professor EOE Pereira Memorial Oration this year. Today, we have gathered here not only as members of a learned society, but as grateful citizens of this country to commemorate the 115th birthday of Professor EOE Pereira, a giant of engineering community. And this event is one of the more important events in the ISL annual calendar. First, let me formally welcome all of you, starting with our guest speaker today, Engineer Professor J.J. Vijayatunga, Head of the Department of Civil Engineering, University of Pereira. Family members of the late Professor Engineer EOE Pereira, who are joining with us today online due to the other difficulties. They are not attending in person, but they are joining online. And then special invitees, past presidents, council members, members of the ISL, joining in person and online. Chairman Civil Engineering Sectional Committee, Engineer Manjula Samarasinghe. Sorry, Professor Tishan Jayasinghe and Engineer Manjula Secretary. Chief Executive Officer, Engineer Neil Abesekara, and the ISL staff. Ladies and gentlemen, ISL, being the premier body for professional engineers in the country, recognizes engineering giants who have rendered a remarkable contribution for the development and well-being of the profession, institution, and finally to the country. Vidyajyoti Engineer Professor EOE Pereira is one such engineering giant in the history of engineering in Sri Lanka. He played a prominent role in the establishment of engineering faculty in the University of Ceylon and is also known as the father of the engineering education in Sri Lanka. Professor EOE Pereira paved the way for all of us to become engineers. We would not have been sitting here as engineers if not for the enormous contribution he rendered to the development of engineering education in the country. He was responsible for putting in place the foundations on which the higher education in engineering in Sri Lanka is built upon today. Professor EOE Pereira was born in 13th September 1907. He received his primary education at the Royal College, Colombo, where he excelled in both academics and sports. He won the Soisa Science Prize, the Muhammad Ali Arithmetic Prize, Evans Prize for Mathematics that he shared with Mr. D.G. Obesekara, and he won House Colours for Cricket. Late President J.R. Jayawardena, the first executive president of Sri Lanka, and Ceylon cricketer N.S. Joseph were his contemporaries at Royal College. In 1928, he entered the University College Colombo and graduated with a first-class honours degree from the University of London, gaining first place in the Faculty of Science and winning a scholarship. The scholarship enabled him to enter Downing College, Cambridge, UK. He gained the distinction of being the only graduate to finish the 3-year degree in 2 years. His contemporaries at Cambridge included the late Mr. Dudley Senanayake, former Prime Minister of Ceylon. From the University of Cambridge, he graduated with first-class honours in Mechanical Sciences, Tripos in 1931. Now let me mention about his career. Vidyajyoti Professor EOE Pereira served in the Department of Public Works for 15 years before he joining the teaching staff of the University of Ceylon in 1946. Called upon to provide leadership
when the country decided to educate its engineers in its own soil, he had to literally start from scratch in establishing the first faculty of engineering in the country. At first, in temporary settings, started at the Ceylon Technical College at Maradana, and then in a shed at Thurston Road premises of the new University of Colombo, before it found permanent accommodation at Pereira at the now Faculty of Engineering premises of the Pereira University. The fact that the University of London decided to withdraw its external BSc engineering degree being conducted up to that time at the Ceylon Technical College made the task entrusted to him all more daunting. Not only did he have to hurriedly scramble the necessary academic staff, but also attend to the acquiring of the most appropriate equipment for the laboratory that was being built at the new faculty, while also overcoming the administrative hurdles thrown across his path. He achieved his goals successfully and reigned as the Dean of the Engineering Faculty for 2 decades before he was given the Vice Chancellorship of that university in 1969 as a crowning glory, speaking volumes of his greatness. He was its first Professor of Civil Engineering and the founding Dean of the Engineering Faculty, University of Ceylon, at its inception in 1950. Then he was the chairman of the National Science Council and member of several other government boards and commissions, including the Official Languages Commission and the Loan Commission. Professor Pereira was honored with the title Vidya Jyoti in 1986 by then government. He died in 1988. Vidya Jyoti Ioyi Pereira, Theatre of the Faculty of Engineering, University of Pereira was named to honor him. In addition to that, there are several awards are made each year in his name. To name few, the Ioyi Pereira Gold Medal at the Faculty of Engineering, University of Pereira, the annual Ioyi Pereira Memorial Prize of the Best Paper awarded by the Institution of Engineers Sri Lanka, and the annual Ioyi Pereira Memorial Lecture that we are conducting today. So with that brief introduction, let me conclude my speech and get into the proceedings. Once again, I wish to extend a warm welcome to all of you who are joining in person today in this hall and the members joining online. Thank you very much.
Thank you very much, Dr. Laksari, the acting president. Let me now introduce our speaker today, Professor Janaka Vijayatunga. Professor Vijayatunga received his PhD in coastal engineering from Cambridge University, UK in 1997 and joined the Department of Civil Engineering, University of Pereira in the same year. He has also been a visiting professor at the Department of Engineering Science, University of Oxford, UK, visiting research professor at the School of Engineering of the University of Southern California, USA, and visiting scientist at Cornell University, USA, during his sabbatical leave. At present, he is the head of the Department of Civil Engineering, University of Pereira. His research areas include wave structure interaction, tsunami and storm surge hydrodynamics, as well as coastal hazard assessments. Professor Vijayatunga was the recipient of the prestigious CVCD Excellence Award in 2014 as the most outstanding senior researcher in technology, engineering, and related sciences in Sri Lankan universities. He also received the Presidential Award for Scientific Research Publications several times, as well as the National Science Foundation Research Award for Scientific Excellence in the field of engineering sciences twice in 2008 and in 2017. Professor Vijayatunga has published over 80 papers in national and international journals and conference proceedings, and his paper on the effects of coastal sediment transport on seabed friction and turbulence received the American Society of Civil Engineers Award for the best paper in the Journal of Waterway, Port, Coastal and Ocean Engineering. He has served in several national level committees, including the Research Advisory Board of the National Science Foundation, Steering Committee on Coastal Hazards, Early Warning at the Ministry of Disaster Management, Standing Committee on Climate Change and Natural Disasters of the National Science Foundation, and Standing Committee on Postgraduate Studies and Research of the University of Grant Commission. Professor Wijetunga has been serving as an invited speaker in several countries and has chaired at the international conferences and has been in a number of international scientific committees. Now let me invite Professor Wijetunga. The memorial oration topic is Coastal Flood Hazard Due to Tropical Cyclone Induced Sea Surges. Over to you, sir.
Good evening, and thanks very much. So Engineer Dr. Kamal Laksiri, President, Acting President and President-elect. Then Engineer Professor NTR Jayasinghe, Chair of the Civil Engineering Sectional Committee, and Engineer Manjula Samarasinghe, Secretary of the Committee, past presidents, members of the Council, relatives and friends of late Professor E.O.E. Pereira, Dean, Faculty of Engineering, University of Pereira, other members of the Civil Engineering Sectional Committee, Engineer Neela Besekara, CEO, and staff members of IESL, all distinguished invitees, my colleagues from Faculty of Engineering, Pereira University, ladies and gentlemen, both here and those who are joining on Zoom. It is indeed a great honor for me to deliver Engineer Professor E.O.E. Pereira Memorial Oration, and let me thank the Institution of Engineers Sri Lanka for inviting me, and its Civil Engineering Sectional Committee for nominating me and for organizing this event. And in fact, as academics and as engineers, we thank our institution very much for paying a tribute to late Professor E.O.E. Pereira, the father of modern engineering education in the country, by organizing this memorial event annually, and this time on the occasion of the 115th birth anniversary of this legendary academic, administrator, and engineer. Now, in fact, on this occasion, let me first take a few minutes at the beginning to briefly touch on some aspects of the lasting legacy of Professor E.O.E. Pereira, who we see in this 1950 photo right here, seated with Sir Ivor Jennings, the Vice Chancellor at the time, and Professor R.H. Paul, with the first batch of engineering students in their first year. And now, in fact, as we heard, short while ago, Professor E.O.E. Pereira had been a great mentor to many, when he was the professor of civil engineering, as well as the dean of the Faculty of Engineering. And in fact, even without his presence, I can say Professor EOE has continued to be a source of inspiration for many generations of engineering educators, practicing engineers, and students, including myself. Now, in fact, at Pereira Engineering Faculty, we are constantly reminded of his foresight and wisdom. Now, for instance, in planning the facilities and the academic program, starting back in the late 1940s through 1950, I think continuing through 1950s and then on to 1960s, with the shift to the permanent place at Pereira happening in 1964. So these extremely well-planned infrastructure, massive laboratories and design offices that we have at Pereira. And, well-designed and built lecture theaters, long, wide corridors, connecting these labs and design offices and so on. And many other features, I would say well thought out and meticulously planned. And in fact, through and in these, we sort of feel his presence in many ways all the time. In fact, in all of these facilities and in the old curriculum, we see his touch, his vision and foresight. And in fact, all of that provide us with a great source of inspiration even today, and I'm sure for many years to come as well. Now, by the way, not everything had been so straightforward and smooth sailing. Occasionally, as one might expect, sometimes, maybe due to financial constraints, may not have fully understood and appreciated his vision at the time of the need to lay that strong base for engineering education in the country, not simply for the immediate or short-term needs at that time, but for many decades to come. And fortunately, he had been able to overcome such hurdles from which we indeed benefit even to date. Now, at Pereira, such efforts of our founding fathers, their foresight and wisdom, together with the core values that they have instilled, are in fact the very solid foundation upon which the Pereira Engineering Faculty has grown and continues to stand stronger. In fact, late Professor Pereira had laid a very strong foundation for excellence in engineering education, not only at Pereira, but for the entire country as well. Now, for instance, graduates of the first Faculty of Engineering had then contributed immensely in setting up of faculties of engineering at Moratuwa and then later at Ruhuna. These three faculties, now we know, are now well established and providing an excellent engineering education to thousands of students. It is also good to see several more faculties of engineering set up in relatively more recent times. For example, in the north, in the east, and in and around Colombo. And it is indeed so pleasing, to see graduates of the three older faculties making excellent contributions at these relatively new faculties. And despite many challenges, they are also doing well and making very good progress. So we are eternally grateful to this great engineer, professor, and the visionary leader for laying that solid footing of engineering education that we continue to build on, as I said earlier. And in fact, we have also heard or read, accounts or anecdotes of the excellent leadership that he has, he had provided with immense integrity and kindness. Many acts of compassion, as well as humility as a teacher, and then as the dean of the faculty, later as the vice chancellor of the university as well. Now, finally, as I understand, pursuing excellence and standing on principles had been two key traits of late Professor Pereira, and he was a professional gentleman to the core and a professional of rare breed who did not handle academic or academic related matters in a transactional manner, instead guided more by what is right and what is wrong in keeping with accepted rules or procedures. So a great academic and a great human being indeed. A man of immense integrity, vision, and courage, late engineer Professor E.O.E. Pereira had been. So we all in the engineering community and the country owe him an immeasurable debt of gratitude for his outstanding service, dedication, foresight, and wisdom always. So with those brief remarks at the beginning, let me move on to the topic of the memorial lecture this evening, which is coastal flood hazard due to tropical cyclone induced sea surges, coastal flooding, caused by sea surges generated due to tropical cyclone action. And in fact, these tropical cyclones or typhoons, hurricanes, it is in fact the same thing, called by different names in different parts of the world. Now, for example, yes, tropical cyclones in this part of the world, in the Indian Ocean region and in the South Pacific, so India, Sri Lanka, Bangladesh, as well as, for example, Australia, we call these rotating weather systems tropical cyclones. And the same thing is known as typhoons in the Northwestern Pacific, for example, in Japan, Korea, Taiwan, the Philippines, and so on. And at the same time, these are known as hurricanes, as you know, in the North Atlantic and in the Northeastern Pacific, for example, USA, and then in the Caribbean islands. But it is the same thing that is called by different names. So just at the beginning, a little very quick look at some characteristics of these tropical cyclones, these weather systems. In fact, as you know, right at the center, we have the eye of the cyclone, and right around the eye wall. And without going into too much detail, but very quickly, if I just touch on the pressure and wind speed distributions within these cyclones. So that is what we are trying to show here, the broken line, the pressure field. You can see that the pressure is quite low at the center, quite low here, broken line, and then gradually increasing radially outwards, and then becoming the ambient atmospheric pressure there. And on the other hand, the wind speed, the solid line here, which is the highest on the right-hand side. So pressure, yes, the lowest at the center, and then gradually increasing radially outwards. On the other hand, the wind speed, the highest in the eye wall, and then decreasing radially outwards. In any case, I don't want to spend too much time on such aspects. Instead, yes, as I said earlier, these are rotating weather systems. And then, obviously, as you know, these tropical cyclones, they move forward, generally, rather slowly, maybe with speeds like 5 kilometers per hour, 10, 20, 30, and so on. And for example, this particular cyclone making right now landfall near Trincomalee, and then exiting the country. So here is a numerical simulation of the pressure field of a past cyclone across Sri Lanka. Right, so with that, if we have a quick look at tracks and intensity of tropical storms over a certain time period across the world, this is, what we see. In fact, as you can see that, these tropical storms, they form between the two tropics. But again, not very close to the equator either. And in fact, one reason they form within the tropics is that, these cyclones need energy provided by the warm oceans. And just to mention one other thing, that is, as you know, these cyclones rotate anti-clockwise in the northern hemisphere, but in the southern hemisphere, these cyclones rotate clockwise because of the Coriolis effect. So this is the picture for the entire world for a certain past time period. But if you have a little closer look at our part of the world, here are the tracks in the last 100 years or so in the Indian Ocean region, North Indian Ocean region. On the right-hand side, we can see cyclones that had originated in the Bay of Bengal, whereas on the left, cyclones that had formed in the Arabian Sea. And very quickly, let me also mention that, different classifications are used to categorize these weather systems in different parts of the world. But here is the typical classification used in India and in Sri Lanka as well, based on the maximum wind speed in kilometers per hour. So depression, deep depression, and then when the wind speed exceeds 62 kilometers per hour, then that weather system becomes a cyclonic storm. And then we have severe cyclonic storms, very severe cyclonic storms, and then even supercyclonic storms as well, depending on the maximum wind speed. This radial, this tangential wind speed. And so then again, getting back to these cyclones in the North Indian Ocean region, as I mentioned earlier, in the Bay of Bengal and in the Arabian Sea, if we just have a quick look at some statistics, the number of cyclones that had formed in this part of the world during this period, more than 100 years. In fact, about 120 cyclones had formed in the Arabian Sea, whereas during the same time period, about 450 had formed in the Bay of Bengal. So much more coming from Bay of Bengal. And then of this 450, that had formed in Bay of Bengal during that period, 57 of that number had made landfall, had struck India. Then 16% Bangladesh, 4% had made landfall or crossed Sri Lanka. And the remaining 15% of the cyclones had dissipated over the sea before reaching a landmass. Now, these are all cyclones, but if we focus on the very severe cyclonic storms with wind speeds exceeding 118 kilometers per hour, in fact, about 1/4 of this number had been very severe cyclonic storms. Then if we similarly, have a quick look at the statistics of that 1/4 very severe ones, then 52% had made landfall in India, 25% in Bangladesh. So in a way, fortunately, our share not as large as India, Bangladesh, and so on, but at the same time, a certain number of cyclones had crossed Sri Lanka as well during that period. So here, in fact, on this slide, we can see the tracks, the paths of the cyclones that had made landfall in Sri Lanka during that nearly 120-year time period. Here is the list starting from 1906, the latest 2020 November, and a relatively, smaller one. And so here are the tracks, as I said earlier. In fact, one thing we see is that most of the cyclones had been formed in Bay of Bengal. So our cyclone threat comes mainly from Bay of Bengal, only very few from the Arabian Sea. And then one other thing to note here is that, yes, the blue ones, cyclonic storms, but the red ones are in fact severe or very severe cyclonic storms. So out of this lot, we see quite a number of red ones as well, severe or very severe cyclonic storms. And then just for a moment, if we focus on the temporal distribution of cyclones in the North Indian Ocean region, again, over a 100-year time period. The frequency, during which months, cyclones tend to form most. In the Arabian Sea, sort of we tend to have this, two-model distribution, like May, June, and also October through December. Cyclones, tend to form. And then in Bay of Bengal, somewhat similarly, like we see two peaks, May, June, July, and then, but mostly October, November, and December. Those are the more cyclone-prone months. And, then, in fact, my topic is not so much about cyclones, but the sea surge and flooding caused by such cyclone action. So let's very quickly have a little look at, how these sea surges are generated due to cyclonic activity. Now, okay, a cyclone, right now somewhere here and moving towards India, right here. And then we can also have a look at this sort of simple illustration, this cyclonic activity on the surface of the ocean. So what obviously happens, as you know, the force of the wind or the wind shear pushing water against the shoreline when the cyclone is near the shoreline. So when the force of the wind shear pushing this water mass against the shoreline, the water level is going to go up. The water level is going to go up. And that is how that surge is created. So the wind should be blowing towards a shoreline against. In fact, I think we were talking about this earlier more about the cyclones, and we were just about to, get into these storm surges generated by the cyclones. So if there had to be an interruption, that was not too bad a time in a way. I mean, so we were just starting to move on to that, only started. So I think as I was telling that, the wind action, the wind force on the surface of the ocean, then pushing water against the shoreline, and as a result, the water level going up, creating this surge. Now, so as a result, the wind has to be blowing towards the shoreline for there to be a surge. If the wind is blowing away from the shoreline towards offshore, there is no surge. Now, let us say a cyclone approaching towards Trincomalee, and then right there, okay, circulating anticlockwise. Then on which side, do we expect a surge? Is it north of the center of the cyclone or towards south? Now, clearly the wind is blowing, towards the shoreline on the north of the side. So as a result, we would expect some surge, on the north of the center of the cyclone. On the other hand, to the south, the wind is blowing away from the shoreline, so there is no surge there. Now this same cyclone, now it is making landfall, and then it is going to exit the country somewhere, says, right there. Once again, yes, cyclone, rotating anticlockwise. And this time, is it to the north or to the south that we might expect some surge? Clearly, wind is blowing towards the shoreline, on the south of the center. So as a result, we can expect some surge on this side. Now, talking about these coastal surges and coastal flooding during cyclonic activity, as this Jubian Murthy, they noted that, in fact, in coastal areas, about 90% of the damage is due to this inundation of low-lying lands by the seawater, sea surge. And the balance 10% of or so, is from the very strong winds. But mostly in coastal areas, the damage is due to this storm surge. Now, if we have a quick look at some of the major, past cyclonic activity from around the world, then first, in the Indian Ocean region, Bangladesh, right there, this cyclone Bola, in 1970, resulted in a 10-meter high storm surge in Bangladesh in 1970, with an estimated death toll. Nobody was quite certain, the death toll estimated death toll ranging from 300,000 to over 500,000 in 1970. Due to that 10-meter high storm surge. And then again in Bangladesh in 1991, a cyclone with wind speeds of 250 kilometers per hour resulted in a 6-meter storm surge. And that time, 138,000 people died. Now, from this part of the USA, Gulf of Mexico region, the southern part, several storm surges from Louisiana right there. Hurricane Camille in 1999, the surge 7-meter high. And then, the well-known Hurricane Katrina in 2005, with wind speeds exceeding 280 kilometers per hour. The increase in water level had been 3 to 8 meters in different parts of the coastline. just only a few examples of such cyclonic activity. And let me quickly move on to just have a, look at the different components of this sea surge due to high winds during cyclonic storms. And this, rise in seawater level during these storms, usually could be due to several different mechanisms. For one thing, due to the low pressure, mainly in and around the center of the cyclone. Low pressure means water level is going to rise, obviously. And then clearly, due to the wind force, the major part of the rise in water level is due to the wind force. And then, in addition to these, okay, let us say that due to low pressure and wind force, from the usual mean water level, now there is the surge, water level is somewhere there, surface of the ocean. And then, of course, during this cyclonic activity, there are very powerful waves formed on the surface of the ocean. Maybe 3 meters, 5 meters, even 10, 15 meter high waves due to the high winds, depending on the wind speed. And then, of course, these, very high waves cannot reach the land itself. Instead, the waves are going to break somewhere. And then, of course, this during the wave breaking, because of that process, there is also a rise in water level. There is also a rise in water level. We can take it as, okay, kinetic energy of the waves. Now, during the breaking process, that kinetic energy is sort of converted to a potential energy. And as a result, water level going up. So there is another contribution to the storm surge due to these breaking waves. Then, of course, in addition to that, we know the tide. Depending on the tide, the water level can be higher or lower. So that is another contributing factor. So as a result, we can identify the total surge sort of, composed of several different components. Now, of course, having identified some, features of cyclones, and then a little bit touching on this storm surge, one very important thing, of course, is to look at, okay, how high these storm surges could be around our country, around Sri Lanka. In other words, assessment of the storm surge hazard due to cyclones around the country. And in fact, I happen to be the team leader of this coastal hazard mapping program 10, 12 years ago for the Ministry of Disaster Management. So I, coordinated 4 coastal hazards, including tsunami and storm surges. So during that time, we started looking into this cyclonic activity. And I can remember those days, there was very little that was available in the literature. So we had to start almost from scratch and then build the knowledge and, find the required information. So one thing that we need to find is, okay, if a cyclone is making landfall somewhere near Vaticolo, how high the surge is going to be. Then let us say the same cyclone, same wind speed, if it is making landfall north of Trincomalee, how high, can we expect this surge to be? Similarly, okay, a cyclone making landfall near Colombo. Is it the same surge? So that is sort of the question that we wanted to find an answer to. In other words, the surge height distribution around the country for a given cyclone and for a range of wind speeds. So to do that, we had to use numerical models. And when it comes to numerical modeling of sea surges, we do that in two parts, in two stages. First, we model the cyclone, and then we model the hydrodynamics of the sea surge, as well as the wave effects. So yes, all starting from the wind speed, wind stress, and then different contributions coming into this calculation. And so we use some of these advanced models, hydrodynamic as well as ocean wave simulation models, dynamically coupled, and also information provided by a cyclone model also coupled in. And in this, we have also made use of these synthetic cyclones based on Monte Carlo simulation technique to generate more cyclones, given the relatively sparse database. And in fact, in more recent times, we are coupling river hydraulics models as well as hydrological models into this setup to take into account such contributions as well, which I will get into a little later. Right, then let me focus a bit on some notable past cyclonic activity in our country. As I noted earlier, about 20 or 22 cyclones had crossed Sri Lanka during the last 120 years or so. Of those, we can identify several very severe ones. So here are two of those, probably the most severe in the last century, 1978 cyclone and 1964 cyclone. So during that study, more than 10 years ago, as I said, we were using numerical models, but we wanted to find out how good these numerical models were. In other words, we wanted to do a calibration or verification. And so we got hold of some past cyclonic activity, 1978 to start with. So we modeled the sea surge due to 1978 cyclone. As you can see, this is part of the East Coast, Batticaloa, Calcutta. And then our model predicted a maximum surge of around 1 to 2 meters in here. And that was in reasonably good agreement with available observations of this 1978 cyclone. That gave us some confidence. And then we also modeled 1964 cyclone as well. This we have seen before, short while ago. This is 1964 severe cyclonic storm. As I said earlier, made landfall near Trinco and then exited near Mannar and then into southern part of India. So when we modeled the storm surge due to this 1964 cyclone, this is what we found. Yes, the cyclone made landfall near Trinco, but hardly any notable surge there at landfall. But instead, what we saw was that apparently there had been quite a big surge near Mannar. So if I, blow up this area, that is what I'm showing right now, this Mannar region. So here is the distribution of sea surge, the height, the water level, and we can see that right there, near Mannar, there had been a surge, or at least a surge of around 4 to 5 meters high, 4 to 5 meters, sort of reminding us of tsunami-like flooding. 4 to 5 meter high surge in Mannar, that is what the model, was indicating. As I said, this is the cyclone that occurred in December 1964. And but then at that time, we did not know. There was nothing much in the literature of this kind of surge in Mannar. So unlike 1978 cyclone, for which we had some information, but for the 1964 one, there was almost nothing at that time. So then I was wondering, okay, if there had been 4 to 5 meter high surge, due to this 1964 cyclone, then that must have been recorded somewhere. I was thinking that then our kind of national newspaper, must have recorded if such an event had happened as predicted by the model. So I can remember, I asked my RA, research assistant at the time, to go to Colombo and dig into National Archives and scan through the newspapers, old newspapers, to see, around about this time, 23rd, 24th, whether there was some news on this kind of surge. And in fact, this is what my research assistant found from the National Archives. These headlines, this one from Lankadeep, 25th of December 1964. Yes, unfortunately, the death toll over 600 due to that cyclone. And by the way, I guess I should not try to translate this bit, right? And then yes, it also indicates that the speed of the cyclone, 150 miles per hour, it is about 240 kilometers per hour. Very, very severe cyclone, super cyclone, in fact. And then further inside of that newspaper, more information about the damage. And then another newspaper, same event on the same day, 25th of December 1964, Dinamina. 200 dead bodies drifting towards India. It must have been fishermen who had gone out to sea, not knowing a cyclone, had been coming their way. And but then, what we were looking for was mostly how high the surge had been in Mannar. And that information we found in this newspaper, Ceylon Daily Mirror, this Gail Havoc. And then inside of that newspaper, we found this description by a reporter of the situation, in Mannar due to that 1964 cyclone. Sort of somewhat old English. If I quickly read through, a fantastic tidal wave rising 15 feet over the land, whipped over the island of Mannar at the very height of the awesome cyclone. Today, 6 days after the event, only a sheet of water subsiding ever so slowly marks the place where once a city stood. The Mannar of Monday, the 21st, no longer exists. And yes, in fact, before I move any further, yes, the information that we were looking for, it is there. The water level rising 15 feet over the land, right here in Mannar. In fact, as indicated by the model, 4 to 5 meters surge height. And then that piece of article, the description, further says that that is this island of Mannar, cut off completely from the mainland. Food for the estimated 3,000 families rendered homeless is being dropped into the stricken city from the air. All wells have been polluted by the filth that poured into them. And then further down, up to now, an accurate estimate of the number of lives lost has been impossible. We can only wait and see. Somewhat, sort of reminding us of the aftermath of the tsunami disaster in 2004. Not surprisingly, this had been, close to 5 meter surge. So the entire city had virtually disappeared because of the sea surge due to this, very severe cyclone. Yes, another newspaper also describing what happened to Mannar. And also let me quickly mention that because of the same cyclone, the sea surge and the waves during that cyclonic activity, somewhat reminding us of the parallel train disaster. This cyclone, the sea surge and the waves also submerged and overturned a train carrying, 150 passengers near Pamban right here. in 1964. Okay, then as I said, the primary purpose of such numerical modeling was to assess the storm surge hazard around the coastline of Sri Lanka. As I said, we wanted to know cyclone somewhere here, how high the surge is going to be. Similarly, same cyclone, let us say 200 kilometers per hour cyclone as an example, how high the surge could be around here or there. Is it the same or is it not? And so, in fact, we did a lot of modeling using these coupled models. And here is a summary of the results of the surge height that we found from these models. This, in fact, for a cyclone with maximum wind speed 200 kilometers per hour, with an estimated return period of about 90 years. So for that kind of cyclone, if it strikes somewhere near Trincomalee, how high the surge is, or if it strikes somewhere near Jaffna Peninsula, how high the surge is going to be. Similarly, same cyclone, if it makes landfall somewhere near Colombo, how high the surge is going to be. That was the intention. And so here are the results. Sea surge height, green 1 to 1.5 meters high surge, and then yellow 1.5 to 2 meters, and then blue 2 to 3 meters, and then 3 to 4 and more than 4, purple and red. So what we are seeing is, yes, most of the East Coast, South and West, you can see green, indicating about 1 to 1.5 meter surge due to a 200 kilometer per hour wind speed cyclone, mostly. But at the same time, we see that in this part of the northern coast, blue, that is 2 to 3 meter high surge due to the same cyclone in here. And then in the northwestern part, we see that due to the same cyclone, the surge height can be as high as 3 or 4 meters, as high as 3 or 4 meters. So quite clearly, even with the same cyclone, same wind speed, the expected surge height is going to be different in different parts of the coastline. And we can clearly see that the hazard, the level of hazard is much higher in the northern part as well as northwestern part. That is quite clear. Relatively less, along the rest of the coastline. But the most of the threat in terms of surge height in north is part of, as well as northwestern part of the coastline. And you might ask why, same cyclone, why is it different in, different parts of the coastline? The answer is, in fact, it is pretty much down to the seabed, shape of the seabed near the shoreline, close to the shoreline, the bathymetry. That is, what I'm showing here, this map, seabed bathymetry, contours 50 meter, 50 to 100 and so on. But let us focus on this shallow part, less than 50 meter, mostly white areas, shallow sea, less than 50 meter. And what we are seeing is, yes, this northern part, this part compared to here, shallow, more shallow, going further away. That, in other words, the continental shelf is wider in, this part of the coastline. And then in here also, you can see that obviously, as you all know, sort of very shallow, this Mana and, that part of the seaboard of Sri Lanka. And on the other hand, in here, not as narrow and shallow the continental shelf. And so if we match, what we found, surge heights, again, we see that where the seabed is shallow, we have higher surge heights. And that is why higher surge heights in the northern part and even higher in this northwestern region, there. And just to add that, we noted that part of the contribution to the surge height comes from these breaking waves, sea waves. Of course, a major component, the wind pushing the water. But in addition to that, as we noted earlier, part of the surge could be due to the wave effect, breaking waves. So we tried to estimate how much is the contribution from these sea waves to the total storm surge. That is what I am showing here, the percentage contribution of sea waves, ocean waves, breaking waves to this storm surge. Less than 5% green, and then yellow 5 to 10%, and so on. So what we are seeing is in the northern part, right there, it's mostly, smaller percentages, relatively smaller percentages, some less than 5% or 5 to 10%. Whereas in some of the other parts of the coastline, certain parts of the East Coast, 25 to 35%, or even higher, 35 to 40%. So, what we are seeing is that if we take Mana right there, where we had a very high surge, but what we are seeing is only maybe less than 5% of that, generally due to sea waves. That we can somewhat expect, isn't it? Because, you don't expect very high waves in this somewhat confined region. And for the wave heights also not that high, so similar reasons contributing to that. Okay, with that, let me quickly touch on another contribution to this coastal flooding during cyclonic activity. As we all know, almost always when there is severe cyclonic activity, there is very heavy precipitation, rainfall. So as a result, not only sea surge, there is, riverine flooding as well because of the heavy precipitation. So it is very important for us to estimate that as well, because in reality, all of these happening at the same time. So, which we call compound flooding. And for that, we had to integrate hydrologic as well as river hydraulic models into our numerical model setup, and which we did. And then we could identify, different flood interaction zones, kind of part of the flooding coming from the ocean. And then, of course, from the land, swollen rivers, overflowing rivers contributing, all combining, interacting. And but I'm not going to go into details right here. Instead, let me move on to, towards the end of my, presentation right now. Very important, part of this kind of hazard assessment, that is mitigation of cyclone-induced storm surge hazard. And for that, let me take as an example, cyclone impact in Bangladesh, which we touched on a little earlier. We noted that in 1970, a very high death toll, over 300,000. And then in 1991, the death toll had been something like 138,000, relatively better, but still quite high. But then in 2007, again, a very powerful cyclone, 260 kilometers per hour, second strongest ever recorded. But the death toll was something like 3,500, which is still high, but compared to the previous numbers, this is a significant achievement by Bangladesh through various mitigation measures. And the primary mitigation measure, in fact, they have the cyclone preparedness program covering 11 districts in coastal areas. And they have over 42,000 trained volunteers and 2,000 cyclone shelters as well. So what these volunteers do is they go to virtually each and every household and make sure that people are evacuated. And I've heard that, some people are a little bit reluctant to leave their homes, but they somehow, even by force, they, make sure that those people are evacuated. And it is through such a process that they have been able to bring such very high numbers down to, somewhat reasonable figure in more recent times. So overall, I would say when it comes to mitigation of cyclone-induced sea waves, very important adequate forecasting of storms, and then providing early warning to vulnerable communities, and then making sure those who could be affected are evacuated. That way we can prevent major loss of life. And for that we need information from hazard mapping, risk assessment, and then of course awareness and education, including public awareness, very, very important, as well as capacity building in these areas. For forecasting and early warning, we have prepared, we have made, various software. Then we have done hazard and risk assessments at Pereira engineering faculty, and for different parts of the country, in fact, for the entire country. Yes, hazard and risk assessments. Then right here for different parts of the coastline, different cities, risk of inundation due to storm surges assessed. And in fact, as I mentioned, this was started more than 10 years ago. Then through that project, the results, hazard maps for storm surges and so on, we have all made those available to the Disaster Management Center. And in fact, that project was coordinated by DMC. And so all these are now available on the website of the DMC as part of the National Hazard Profile. I mentioned awareness and education also very important. And for that, I have written some articles in Sinhala as well as in English to make the general public more aware of, coastal flooding due to cyclonic activity as well. People are now quite aware of coastal flooding due to tsunami, but at the same time, it is very important for us to make them aware of similar coastal flooding, somewhat similar coastal flooding due to cyclonic activity as well, the potential for that. And then in some other countries, various, as you know, engineering works, storm surge barriers and so on, and gates, and and then just to add here that all of that, they have developed a numerical simulation facility in the Department of Civil Engineering, University of Pereira, for modeling these tsunami and storm surges. And I must acknowledge funding for all of these received from the National Research Council, National Science Foundation, as well as the Ministry of Disaster Management. And then, in fact, we have been providing advanced information to the Disaster Management Center whenever there is cyclonic activity in our country. During that period, we haven't had any severe cyclonic activity, some low-level cyclonic activity only. One was in January 2014. There again, we modeled and provided these predicted surge heights to the DMC. As you can see that less than 1 meter, so it's not felt that much. Yes, again, the same thing. But again, we see that it's, mostly in Mana area that we, sort of that part of the coastline, we tend to see relatively higher surge heights. And then in more recent times, in November, December 2020, Cyclone Burevi that made landfall in Sri Lanka, this cyclone right here. And there was some damage in, again, Mana, that island. So once again, we modeled and provided this information to the DMC in advance. This time, little bit higher surge levels, going up to 1.5 and 1.8 meter like roughly. And we thereafter made some field measurements after the event and found these estimates to be reasonably accurate. Okay, now finally, before I conclude, just a few remarks and the way forward when it comes to this coastal flooding due to cyclonic activity. So, as we noted that several severe cyclones have hit Sri Lanka in the past century, and those in 1964 and 1978 being the worst, resulting in loss of lives of the order of several hundred, as well as considerable damage to housing and other infrastructure. Then in comparison, death toll in Sri Lanka due to the tsunami, as we know, tsunami in 2004, that was of the order of several tens of thousands, much more. But a tsunami event of that magnitude is extremely rare, fortunately. Generally expected only once every several centuries. So what we are seeing is tropical cyclone-induced storm surges, seems pose a more frequent compared to tsunami, a more frequent hazard compared to tsunami, but of course, perhaps comparatively less severe generally, as far as threat of flooding in most parts of the coastline is concerned compared to tsunami. So what I'm trying to say is that in terms of kind of severity, in many parts of the coastline, hopefully it's not as severe as tsunami, but then tsunamis are expected, once in several centuries. But this cyclone-induced coastal flooding, which can be much more frequent. For example, we have had more than 20 cyclonic events in the last century, with 4 to 6 being very severe. And so as a result, we need to pay due attention to coastal flooding due to storm surges as well, in addition to tsunami. So I would say that while improving our tsunami preparedness, which we have done to a good extent, we must also pay attention to the potential threat of coastal flooding due to these cyclone-induced sea surges as well. Now, how can the country prepare itself for a severe cyclone event? As far as sea surges are concerned, as we noted earlier, forecasting of storms, early warning, and evacuation are very much necessary to save lives. And then just like in tsunami mitigation, public education and awareness is also a very important, part of storm surge hazard mitigation as well. So I would say it is wise or prudent to integrate cyclone-induced storm surge hazard with the tsunami hazard as part of, a multi-hazard risk assessment, which has in fact been done. And so through this research and other work, we have generated quite a lot of knowledge and understanding of this storm surge hazard for Sri Lanka with funding from NRC, NSF, and DMC. So it was an original and important study as far as Sri Lanka is concerned. And the work is continuing with more advanced, aspects included, as well as, use of more advanced tools. And in fact, the outcome of these studies, has already made a significant impact on local disaster management planning and preparedness, as well as creating awareness in regard to cyclone-induced storm surges. One very important thing was we were able to mainstream or institutionalize cyclone-induced storm surge hazard also as part of our country's disaster risk management plans. So with that, let me conclude my lecture. And so I'm very grateful for all of you, those who are here, as well as those who are joining on Zoom, for your kind attention. Thanks very much indeed.
Thank you very much, Professor for sharing new knowledge on natural disasters while experiencing man-made disasters today. Hope you all have gained a better understanding of the subject matter. It's of course very much interesting for me personally. Thank you very much, Professor. Now I cordially invite Acting President Dr. Kamal Laksiri to give away the token of appreciation to Professor Vijayathan. Thank you very much. To wind up the session, now I cordially invite our Secretary to the Civil Engineering Sectional Committee, Engineer Manjula Samarasinghe, to give away the vote of thanks. Over to you.
President-elect of the Institute of Engineers Sri Lanka, and acting president, and the members of head tables and fellow engineers joined physically, and the members joining Zoom and online. It's a great honor and privilege to have this opportunity to propose the vote of thanks on behalf of the chairman, Engineer Professor M.T.R. Jayasinghe of the Civil Engineering Sectional Committee, and on behalf of the Committee of Civil Engineering Section Committee. And ladies and gentlemen, the Institution of Engineers recognize such lasting legends by having this kind of memorial presentations. The institution has, I think, 6 memorial presentations of this calibers. We consider Vidya Jyoti engineer Professor E.A. Pereira as the father of engineer education in Sri Lanka. So this is a very special day for all of engineers in Sri Lanka. With these remarks, ladies and gentlemen, I take this opportunity to thank the institution, the president, and the council of the Institute of Engineers for conducting this memorial oration for the 35th time continuously. And remember, even with the COVID period also, we could be able to conduct this presentation. And this is the 35th time. And I must thank the Civil Engineering Section Committee, Engineer Professor M.T.R. Jayasinghe, and the committee for proposing this, our guest speaker today. And I must thank our deep sense of appreciation, Engineer Professor Janaka. Thank you very much, sir, for accepting our invitation for this presentation. And I must thank the Secretariat with CEO, Engineer Numerical, and the team for all the arrangement for this memorial oration. And ladies and gentlemen, I remember when before 2021, when there are orations, we can see all the seats are full, but with this COVID situation and later with this situation of the country, we can see less physical presence, but we can see big presence in online. But today I must especially thank all who came here physically, and we can see the past president, Engineer Piyad Silva, Engineer Chula Silva, Engineer Danpala. Thank you very much. And we can see a few council members here. Thank you very much all, and all the members, fellows. And thank you very much for your presence. And thank you very much those who joined with online for this memorial oration and all the supporting works done by the Institute of Engineers Sri Lanka. And with these remarks, ladies and gentlemen, we invite all of you to join with the fellowship and dinner. which is arranged at the members' lounge at downstairs. And have a good night and safe journey back home. Thank you.